Thank you for joining us this morning on this webinar on analog I/O scaling. The presentation itself is roughly about 20 minutes. Again, if you have any questions at any point, feel free to put them into the chat and we shall get to them at the end.
Welcome to today's tutorial. Let's get started. Let's take a look at our agenda. We'll start by discussing what analog scaling is. We'll discuss how analog data is scaled in Horner automation products, specifically our all-in-one controllers and our remote and expansion I/O. We'll discuss scaling logic using both engineering units and the PID instructions. There will be some demonstrations, and we'll finish with a live Q&A session. So what is analog I/O? Analog I/O are sensors and actuators whose real-world operation utilize numeric values beyond on and off, such as temperature or percentages. Analog scaling is then the conversion of OCS analog to digital data and digital to analog data to and from engineering units. Analog inputs are typically from sensors, and most sensors convert a real-world measurement into a linear electrical signal. 4 to 20 milliamps is the most common, but you'll also see 0 to 20 milliamps, 0 to 10 volts, 0 to 5 volts, and several others. The OCS analog input circuitry converts the linear signal to a numeric value reported in a %AI register. The user's application then converts the %AI numeric value into engineering units, such as bar, inches, etc. Temperature sensors are handled differently because the circuitry that converts the sensor into temperature is built into the OCS. The OCS then reports a value to a %AI register that is pre-converted to temperature. The user may need to use math to scale the %AI value to appropriate temperature readings. Analog outputs work in the opposite way. The user's program determines the desired setting for the analog actuator and then scales the setting to a numeric value. The OCS digital to analog converter converts the numeric value to an electrical signal, which the actuator then converts to an action. Most general purpose sensors put out either 4 to 20 milliamps or 0 to 10 volts. And then for the OCS conversion, 4 to 20 milliamps has 32,000 counts at full scale, which is 20 milliamps. 0 is minimum scale, or 4 milliamps. If your sensor is putting out a signal below 4 milliamps, but above 0, you'll see a negative value. And if your sensor is a bit over 20 milliamps, you'll see a value slightly bigger than 32,000. With voltage, 10 volts is 32,000, and a minimum of 0 volts is 0 counts. You may get a little bit over 32,000 as well. So that's the basics of how analog data is scaled on the input side. The analog input resolution varies between products, but the analog input scaling is the same on most products, with the smart rail as the exception. For units with lower resolution, integer values will increment or decrement by a larger number on a signal change. You can see these on screen. For example, with 16-bit resolution, the minimum change is 1 count. We won't spend a lot of time on this chart. The chart shows you the scaling on the resolution of some popular Horner automation products, from the Micro OCS to our most popular XL series I/O options, the Model 3 and the Model 6, to the Smart Rail and the Smart Block. The Smart Block is our premium analog product, so if you require the highest resolution and the highest isolation, etc. from an analog perspective, the Smart Block is our best product. Okay, now let's look at an example of a pressure sensor that's connected to one of our OCS products. The sensor is monitoring pressure in a range of 0 to 10 bar with an input resolution of 0.01 bar and an output of 4 to 20 milliamps. As we've already covered, 32,000 counts is going to be 20 milliamps or 10 bar, and 4 milliamps is going to be 0 counts or 0 bar. There's a linearization equation, which is how we convert from counts to bar, and then if we go through the math, we see that the end result is 4.23 bar. So that's getting a pressure reading inside your application from a sensor. The second example is the same case, but using a smart rail. So instead of 32,000 counts being full scale, 4,000 counts is full scale. Our linearization equation is slightly different because our full scale is different, but the final pressure reading on the sensor is the same. Now we look at an ultrasonic level sensor, which has a range of 1 to 25 feet. 32,000 counts is going to correlate to 25 feet, and 0 counts is going to correlate to 1 foot. Our linearization equation is slightly different. If we have a sample reading of 7,228 in our AI register, we'll end up at 6.42 feet, or 77.1 inches. So again, these are just different examples of scaling. Now we'll look at a proportional valve where the input to the valve is the signal. So the input is 4 to 20 milliamps, and the output of the valve is its position from 0 to 100%. At 0 counts, the valve is 0% open, and at 32,000 counts, it is 100% open. The linearization equation is very straightforward, and if we want to move the valve to 48% open, we need to set our AQ register to 15,360. So that was the proportional valve output. Now we'll talk about temperature sensors. There are two approaches that you can use. You can use external temperature transmitters to convert to a linear value and follow the same scaling approach. Or you can connect the sensor directly to the OCS analog input circuit compatible with that sensor. Then perform some math to convert the temperature value in the AI register to the desired format. I'm not going to go through this entire chart. This shows some differences between different temperature sensing capabilities with different Horner products. The micro OCS supports RTD, but only a limited range of -50 to +200 Celsius. If your application is beyond that range, you'll need to use an external temperature transmitter. All other models have the same input range, but there are minor differences with other details. This chart is about thermocouples. Thermocouples aren't supported directly in the micro OCS line, so you'll need to have an external temperature transmitter. There's varied specifications for thermocouples within the Horner OCS product line. Now this is an example of an RTD input connected directly to the XL Series Model 6 or a smart rail. Let's say we have a Platinum 100 ohm sensor connected with one AI count of 0.1 degrees Celsius or Fahrenheit. If you select degrees Celsius and you have a value of 100, that means 10.0 degrees Celsius. And if you want to take that value and convert it to Fahrenheit, you'll need to do the equation on screen in your OCS. Let's say we have a thermocouple connected to the XL Model 5. Let's say it's a thermocouple Type K sensor configured for 120 degrees Celsius in Cscape. With the Model 5, you don't have the choice of Fahrenheit. It's already scaled to temperature in 20th of a degree Celsius increments. So you can divide the value by 20 to get your degrees Celsius. You can then use the conversion equation on screen to convert that to Fahrenheit values. Now let's say we're using an RTD PT100 sensor with the micro OCS. Its range is limited to -50 degrees to +200 degrees Celsius, with between -1000 and +4000 counts. To get degrees Celsius, you divide by 20, and you have a simple conversion to get to degrees Fahrenheit. Now we'll discuss analog inputs in logic. There are two ways you can use the scale function. First of all, you can use it in integer mode, which will round off the result. However, you can use implied decimal points. For example, with a 4 to 20 milliamp sensor that's 10 to 100 psi, we can scale 0 to 32,000 to 10 to 100 with two implied decimal points to record values from 1000 to 10,000 instead. The other method is using real mode, where you'd first convert the %AI value from int to real. The result will give you a real value in IEEE floating point format. To scale analog outputs in logic, the process is the opposite. As you can see from the example, we start with the real value for our output command, then scale it to a real value between 0 to 32,000. Then we convert the scaled value to an int and send it to the AQ output. So that's pretty straightforward. Now we'll discuss some tips when using the PID instruction. The Cscape Advanced Ladder PID instruction is an integer instruction which works really well. For process variables with a minimal value range, we recommend scaling the values up to use the whole 0 to 32,000 range. For example, if the PID process variable originates from a pressure sensor of 0 to 10 bar and the expected range is 4 to 6 bar, 4 bar is at 12,800 counts and 6 bar is at 19,200 counts. You should scale the process variable to a larger number of counts, preferably from 0 to 32,000 for the best results. This will increase the range of your values. Now we're going to demonstrate analog scaling in Cscape. Let's start by looking at our OCS in the overhead view. I've got my XL7 and I've got my I/O simulator connected. We're simulating two different analog input sensors which both have a 4 to 20 milliamp output. The first sensor is an ultrasonic sensor that is measuring from 1 to 25 feet, so the minimum is 1 and the maximum is 25. The other is a pressure sensor, which is providing pressure between minus 100 and plus 100 pounds per square inch. Okay, so at this stage, I'm just showing the raw counts for these particular signals coming into the OCS. So let's do some logic to turn these raw counts into the actual engineering units. Let's go to Cscape. So we're in Cscape, and we're going to create a new rung. So I'll drop an always on contact here, and then I'll right click on the power bar and click New Rung. And for this ultrasonic sensor, we'll stay in the integer form. We won't be converting it to floating point. So I can jump right into my scale block. It's located under the advanced math section here. So I can select my scale block and I'll go ahead and drop it on my screen. So what's the input of my scale block? Well, the input of my scale block is the converted signal coming from the sensor that's coming into analog input number 1 or %AI1. Down here, I have created a variable. It's called Ultrasonic and it is an integer based variable. I have the ability using the program variable table to map certain variables. And in this case, I want to map this variable called Ultrasonic directly to %AI1. And then while we're here, I'll show you that I've also mapped another variable called Pressure into AI2, and that's going to be my minus 100 plus 100 pressure sensor that we'll get to later. So we'll start with scaling this ultrasonic sensor. So our input is going to be the variable called ultrasonic. It is mapped directly to %AI1, and the minimum range coming into that value is at 4 milliamps, and it's 0. At 20 milliamps, we're going to be looking at 32,000. Now, what's my output going to be? Well, I need to create a new output variable that is scaled to my engineering units. And my engineering units are going to be in feet. So anywhere between 1 and 25 feet. So let's go ahead and create a variable called tank level. The first thing you need to do when you do a scaling element is select the format that you're looking for. So I need to select integer here. So ultrasonic is an integer variable. Tank level underscore integer is an integer value as well. So since I'm creating this new, I need to press the right arrow key here, and the check mark allows me to create this on the fly. I do want it to be an integer, and it being a global variable is perfect, so I can say yes here. As my value for my sensor comes in from 0 to 32,000, I would be doing the conversion to feet, but I'd be chopping off everything after the decimal point. So I would only have a resolution of 1 foot, and that's not what I want. In this case, if I just add a couple of zeros on my input side and my output side, now I'm going to be scaling from 0 to 32,000, coming in to 100 to 2500. So effectively, I now have a resolution of a 100th of a foot, which is much more precise. So I'll click OK, and then I'm going to go into my user interface here. I'm in my user interface now. I've copied this data object, and I'm going to go ahead and modify this. I still need this in the decimal form, but now my variable is different. Alright, so I'm interested in tank level int, which is the variable that I created, and then when I display this, it'll no longer be in counts, it's in feet. And I can show a decimal point on the screen, even though technically it's just an integer value. Alright, I think that's the way I want it. So now when I display this, I won't just be seeing counts, I will also be seeing the ultrasonic reading down to a 100th of a foot. So that's how I did scaling without even leaving the integer form. Now, let's work on our pressure translation. But this time, we'll do it in floating point. We could do it in integer as well, but let's do it in floating point for illustration purposes. So I'm going to be creating another rung, and again, in Cscape, you can't directly connect a function block to the power rail, you always need at least one contact, so we'll use the always on contact. Now, before I can do my scaling block here for floating point, I need to take that analog input coming in that variable that's currently an integer, and I need to convert that to a real value. So I need to use a conversion operation from integer to real. I'll drop that on the screen. The input, or the integer, in that is the pressure sensor that's mapped to %AI that I've already created. Now here's where I need to create a new real variable, and we'll call this pressure real. So I'll hit this button here because I've yet to create the variable, and I need to make sure that the variable is in the real format. Everything else here is fine. I can click OK, and now I've taken the pressure reading coming in from my analog input, I've converted it to another variable that happens to be real. Now I can go and grab my scale block. We'll make sure that it's the right form, and I do want this to be real this time. So the input of this block is going to be my pressure real variable that I just created. Okay, now it's coming in from 0 to 32,000 counts, and it's going to go out from -100 to +100. However, I still need to create a new variable for the scaled version, and this time we'll call it vessel underscore pressure underscore real. It's a real variable, so now we'll create this variable. That was all the logic that was required here as well, so now that we're done our logic, we'll head over to our screen. So I'm in my screen, I'll copy and paste this so I don't have to create it from scratch. We'll get it lined up. Now let's go ahead and switch first to a 32-bit value. And then we'll switch to a floating point format. And then finally, we'll select our variable, which is vessel underscore pressure underscore real. Okay, again, we're not in counts. This time we are using PSI. And in our legend, it could still say pressure, but I'm going to change it to say vessel. Okay, so this is -100 to +100, and I need to get that data to display properly. So let's say we want to display 3 on the left and 2 on the right, so we'll pick that one. Alright, now it's ready to be downloaded. So we can go ahead and download this program to our controller. Now we'll go back to our OCS and skip to when the download is completed. So we're in our OCS. Let's start with the ultrasonic sensor. Alright, I'm at 360 counts, so we're looking at the left side. We're nearly at 0, but we're not quite there. And as I increase that value, you can see, as our counts go from 0 upwards, our distance is incrementing, to the point that if I continue all the way up to the maximum here, we're going to see a maximum of 25 feet at 32,000 counts. And then similarly with my pressure, I'm looking at a low pressure scaled from -100 to +100. I'll start adjusting the pressure. We're at around 370 counts as we start adjusting this. As I increment up, we get what we want. We're finally going into a positive pressure as we're approximately mid-range. And then if we go again all the way up to the top, we can see that we're at full range and we're at the value that we're looking for. So you can see we use two different approaches here for analog scaling. That concludes today's tutorial. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, just one or two questions in at the moment. I have an XL7. What is the full range? So there's 0 to 32,000. Where can I find the scale block? I believe this came in just before the demo. It is under Advanced Math in the project toolbox. Is there anything else? Not that I can see at the moment, so I shall do the usual and take you back to my screen, which hopefully you can all see now. So next week we have compare functions, followed by part 3 of our IEC support videos. The week after, and as you can see, it carries on down to high-speed outputs and then trends at the beginning of March. All our past ones are here as always. If you do need to go back at any point, they get uploaded on the same day. So this video will be up there at some point later today. So if you do wish to watch it back, you can do so. I think that's about it for today. I don't see any more questions in. Thank you for joining us again. And we hope to see you again next week. Thank you very much.